In December last year, the now Minister of Research and Higher Education, Oddmund Hoel, together with the Minister of Justice and Public Security, visited San Francisco to look into AI. A highlight of this trip was the half day they spent at the Kavli Center for Ethics, Science and the Public at the University of California, Berkeley. There they met Professor Stuart Russell, who co-chairs this Kavli Center. Professor Russell is one of the world's leading researchers in AI, and I am proud to present him as today's keynote speaker. He's also a professor and formerly chair of electrical engineering and computer sciences at UC Berkeley, and professor of computational precision health at UC San Francisco. Professor Russell, we are looking very much forward to hearing your thoughts on the development of AI and the importance of researchers' engagement with the public. The floor is yours.
So thank you very much for the introduction. I am honored to be here, and I'm really looking forward to the conversations that we're going to have today. So let's begin at the beginning. What is artificial intelligence? So obviously it's about making intelligent machines, and that's been a dream of mankind for at least 2,500 years. What we have learned about what that means is this notion, which was borrowed actually from economics and philosophy, the notion of the rational entity. An entity that is intelligent to the extent that its actions can be expected to achieve its objectives. And this is a way in which we measure the rationality of human beings, and we can also apply that concept to machines. So just to give you some examples, right? So AlphaGo, which plays the game of Go, has the objective of winning the game, and it is trained to do that and does its best. When you are driving a car and you use your navigation software, the objective there is to reach the destination at the least cost, and so the AI part of that finds the shortest route to the destination. Something that people are doing now is actually creating fully automated corporations, and they simply give the objective of generating financial return to the shareholders. So this sounds very reasonable, right? We're very much in control, we're specifying the objectives, and off we go. But AI has a more ambitious objective than that. To create general-purpose systems that can exceed human intelligence along every relevant dimension, that whatever environment you put them in, whatever the objective is, they can quickly learn to do a superhuman job of achieving that objective. And here's a question which 5 years ago nobody would have asked. But recently, my co-author Peter Norvig, with whom I wrote the textbook, published a paper saying that we have succeeded. That in fact, the systems we have now, like GPT-4 and Gemini, are real general-purpose intelligence, in the same sense that the Wright brothers' airplane was a real airplane, right? Airplanes got bigger, they got more comfortable, they have better alcohol, but it's the same basic idea. And his argument is, we already have the ideas that we need, we're just going to scale it up, make it bigger and more comfortable. I disagree with that vehemently. I actually think there are major breakthroughs that still have to happen. I would say that these systems like GPT-4 and Gemini, the GPT-like models, are a piece of this puzzle. But the problem is, we don't understand how they work. We do not know the internal principles by which they're able to generate the intelligent behavior that they exhibit. So we're in this very odd situation where we've made a scientific advance, but we don't know what it is. And that makes it difficult to build on it, because we don't know what pieces are missing. We don't know exactly what the capabilities of these systems are that could be coupled with other parts to make a real general-purpose AI system. So we're a little bit like the situation, coming back to alcohol, where 6,000 or 7,000 years ago, someone left a bowl of fruit out in the sun and then came back and drank it and got completely drunk. And they thought, wow, this is marvelous, but we have no idea what's going on and how it works. That's sort of the situation we're in right now. So let's go back a little bit and say, okay, now we know what AI is, how do we make it? So an AI system, very simply, is a box that takes input from its environment and produces behavior. And the question is, what goes in this box so that the behavior is actually intelligent? And there have been a number of answers during the history of AI. Here's one from the 1950s, that we fill the box with Fortran programs. How many people recognize Fortran programs? A few, yes, the bald ones. And what they would do, they would fill it with Fortran programs and then do evolution with those Fortran programs. So they would make mutations to the programs. They would take pairs of programs and mix them together to produce new programs. And this worked absolutely terribly. It completely failed to produce intelligent behavior. On the other hand, they were using about 1 billion times less computation than we use today. And we actually don't know what would happen if we tried this again today. So for most of the history of the field, we adopted an approach that was very much an engineering approach. We tried to understand the principles by which intelligent behavior can be produced, and then turn those principles into artifacts for reasoning, for planning, decision-making, learning, and so on. And the key part of this period of AI was the idea that AI systems should know things. And that knowledge could be represented in mathematical logic or in more general probability theory. And that technology actually produced some really wonderful artifacts. But around 2010, that all changed. And a technology that had been gestating since the 1950s suddenly exploded. And that technology we call deep learning. And there, we simply fill the box with circuit. And so each of these nodes is connected to other nodes by little connections. And the strengths of those connections are adjustable. And by adjusting the strengths of those connections, we change the behavior that comes out the end of the circuit. So it's a very, very simple principle. But to give you a sense of scale, if we took GPT-4 on the scale that I'm showing you here on the screen, which is sort of like a chain link fence, it would be about 100 kilometers by 100 kilometers. So it would cover the whole of the southern part of Norway. But the principle actually is even simpler than the one we did with the Fortran programs. There we did small random mutations and crossover with pairs of programs. Here we just do the small random mutations, about a quintillion small random perturbations of those connection strengths to get the behavior to fit the training data that we supply. And that could be for training data with images, recognizing what's in the images. It could be recognizing the content of speech. Or with the large language models, it's predicting the next word in a sequence of words. So deep learning has produced some amazing advances. And I'll just talk about a few of them. probably the most significant from the point of view of science, is a near-perfect solution of the protein folding problem. So the problem here is that we know for any protein the sequence of amino acids that constitute that protein, but we don't know how to predict the structure. And until recently, the way you did that was X-ray crystallography, which was very difficult, expensive, time-consuming, typically 1 PhD per protein. And it didn't work for a lot of proteins that can't be crystallized or whose structure is significantly modified by the crystallization process. And I'm sure there are chemists in the audience who can tell me that I'm not describing this correctly. But the effort by DeepMind with the AlphaFold sequence of systems produced predictions based on data and machine learning that are sufficiently accurate that for millions of proteins, we now can predict their structure without doing those X-ray crystallography experiments. And biologists tell me that it's like a new candy store that they get to go and play in. A related but quite different advance is the use of deep learning for the simulation of physical systems. So here we're actually predicting how a physical system will evolve over time, or other properties, for example, the stresses and strains in a mechanical system. Here, showing part of a simulation of a COVID virus interacting with aerosol water droplets. My understanding is that this is about a 1 billion atom system, and able to simulate this interaction fast enough to iterate many times in a day, whereas I think with classical simulation systems, this would have taken years of computation time. And simulation is an absolutely central part of many branches of engineering. So simulation of structures allows us to evolve structures. So going back to the same idea that we saw with the Fortran programs, instead of programs here, we're evolving physical structures to optimize for weight and strength and resistance to various forces. And interestingly, we see that the structures that evolve actually look more like biological systems than like mechanical systems. I think we're also going to see significant advances in robotics. So here's a warehouse robot that Amazon is trying out. They call it supporting the human workforce, but actually if you look at it, it's doing the same job as the person. So Amazon has over 1 million people doing this kind of work in warehouses, and the goal is quite clear, to replace them with machines so that reducing cost and increasing capacity. Another kind of robot that we have been waiting for a long time is the self-driving car. And in San Francisco, it's now common. Tourists used to come and ride on the cable car in San Francisco. Now people come and ride on the automated taxi in San Francisco. So it's become a relatively normal part of life. You can just, you have an app, you call the taxi, it comes with no driver, delivers you to where you want to go. But this is partly because San Francisco has been completely mapped in 3D, and there's an enormous amount of background computational work that is not done by the taxi itself that enables the taxi to drive successfully. But even so, every so often something like this happens, where here the taxi drove into some wet cement and got stuck. And this is the problem. Why have we been waiting so long? Because to drive successfully, you need about 8 nines of reliability. And getting 8 nines of reliability means dealing with all of these strange corner cases that happen in the real world. And the AI systems are simply not up to the job as yet. So in controlled environments, this can work, but in completely unstructured environments, and certainly in cities that are less well mapped and less well signposted than San Francisco. I think we're still years away from that. So among some of my colleagues, there's the view that deep learning, as I said, is already the answer to all the questions. But in fact, there are reasons to think that the deep learning, as it's practiced, actually doesn't solve the problems of AI. And here I'm going to get a little bit nerdy and say, look, if you have a circuit like the one I showed you in the box, right, it's what we call a linear time computation system. So the amount of computation that gets done is exactly proportional to the size of the circuit, because the signal comes in at one end, passes through the layers of the circuit, comes out the other end. So what does that mean if you're trying to solve a computational task that cannot be solved in linear time? And there's a whole category of problems we call the NP-hard problems, where we know, or at least we're very, very confident, that they require exponential time to solve. So what that means is the only way that deep learning can solve those problems is for the circuit itself to be exponentially large. And that means that it's going to require an exponential amount of data to train that circuit. And you now have an exponentially large circuit, which requires a huge amount of energy, as the Prime Minister mentioned, to do those computations. And so in practice, rather than build exponentially large circuits, which would be vaster than the universe, we end up approximating these functions. The systems are not actually able to learn these functions correctly. Even though they're very simple to describe, the systems are not able to learn them. And I'll give you an example. So in 2017, AlphaGo defeated the human world champion. His name is Ke Jie from China. And this was regarded as China's Sputnik moment. This was the moment where China decided that it needed to lead the world in AI, otherwise it would be left behind. And since then, Go programs have gone far beyond the human level. So right now, the best program is called Kata-Go. This is a particular version called JBX Kata 005. Its rating is 5,200. The human world champion rating is about 3,800. So it's massively superhuman. It would expect to win 99 or 100 times out of 100 against the human world champion. But I'm going to show you a game between a graduate student from Montreal, who's a member of our extended research group, Kellen Pellerine. He's an amateur Go player. His rating is about 2,300. And he's going to play against Kata-Go. And he's going to give Kata-Go a 9-stone handicap. So if you know anything about Go, a 9-stone handicap is a massive insult. It's treating Kata-Go as if Kata-Go were a 5-year-old just learning to play the game. So in Go, you take turns putting down your stones. The idea is to surround territory and to surround your opponent's pieces. If you completely surround your opponent's pieces, they are captured and removed from the board. Now you know how to play Go. So let's look at the game. So remember that the computer's playing black starts with this massive advantage, and Kellen is playing white. And keep an eye on what happens in the bottom right quadrant of the board. So white is beginning to make a little tiny group of stones. And then black very quickly surrounds that group to stop it from growing. And now white starts to surround the black group. And interestingly, black does not notice this. Black has many opportunities to rescue those stones and connect them up to the rest of the board, but simply fails to observe that it's going to lose those stones unless it does something, and then it loses those stones and loses the game. So this is an elementary failure by a system that is supposedly superhuman. And the reason seems to be that it has failed to learn the basic concept of Go, which is a group of stones. It doesn't seem to understand that that group of stones is a group, maybe because it's a circle. We actually trained a version of Catago specifically to recognize this problem. So we gave it lots and lots of examples of circular groups where we were about to capture them, and then it learned finally to defend those circular groups. But then, lo and behold, when you make a group in the shape of a figure of 8, again, it doesn't recognize that that's a group of stones and allows us to capture it. And so there's a fundamental failure here of the deep learning systems to learn relatively simple concepts correctly. And we see this with the large language models, which despite millions of examples have not learned to do arithmetic. So they cannot add and multiply numbers of arbitrary size. And in fact, what it looks like is that each time we make the network 10 times bigger, they get 1 digit better at doing arithmetic. And so that's the characteristic one would expect from a lookup table rather than from a system that's actually learned the concept correctly. So at the moment, and here's a diagram taken from a pretty important document called Situational Awareness by Leopold Aschenbrenner, who was at OpenAI. The leading companies and the experts within them are predicting superhuman AI before the end of this decade. And they base this on what they call scaling laws, which refer to the improvement in performance as a function of the amount of data and the number of parameters and the amount of computation that's done. And here are some reasons, I think, which would suggest that this will happen. One is that the R&D budget is about 10 times the size of the Manhattan Project. If you're a physicist working on nuclear physics these days, it's 100 times the annual budget of the Large Hadron Collider project. So that gives you a sense of scale. And that money causes very many smart people to be working in this area. And I think many of them realize the weaknesses of simply scaling up these giant circuits, and they are trying lots of other ideas. So I would not want to rule out the possibility that further breakthroughs will occur. On the other hand, we are running out of real data, so we probably maybe get one more order of magnitude of scaling of language models, but beyond that, we have used up all the text in the universe. A second reason why it might not happen is that the investors run out of patience. That's already happened with many of the self-driving car companies where the progress did not justify further investment. According to Goldman Sachs, there's about $500 billion that has been plowed into creating AGI so far. And at some point, people will say, where's the beef, right? And if they lose patience, then we could see another AI winter much bigger than the one we experienced in the late 1980s. So I'm not going to give you a prediction about which of these eventualities I think will come to pass, but I think we have to acknowledge that whether it happens in this decade or in some future decade, we are going to succeed in creating superhuman general-purpose AI. And it's worth remembering why we were doing this in the first place, besides the fact that it's really cool. If we had general-purpose AI, then by definition, we could do what human beings have already managed to do. And as I mentioned last night, our ingenuity as humans has created a civilization where hundreds of millions of people get to enjoy an objectively splendid style of life, as I put it. But we could use AI to do that for everybody because we can do it at much greater scale and at much lower cost. And that would be roughly a 10-fold increase in the GDP of the world, and the net present value of that, so the cash equivalent, therefore a lower bound on the technology value of AGI, would be $15 quadrillion. So that gives you a sense of what is pulling us forward, a giant magnet in the future. And the closer we get, the stronger the force from that magnet. And of course, we could do more things. We might have much better health, much better education, much better science, almost any other thing you can think of. So potentially a golden age for humanity. An obvious issue is, what are human beings going to do when AI systems are doing everything for them? This is from Wall-E, and pointing out one obvious problem. This is Alan Turing. He pointed out another obvious problem back in 1951. He said, "It seems probable that once the machine thinking method had started, it would not take long to outstrip our feeble powers. At some stage, therefore, we should have to expect the machines to take control." Okay. And I think, as the Prime Minister mentioned, this is the question that he had in his mind. How do we retain power over entities more powerful than us forever? And when you ask a question that way, it actually seems a little difficult, right? We don't have a lot of good examples of this happening in the past. But I think it's better to ask it a slightly different way, because we get to choose how we design the AI systems. So what is a mathematically defined problem? How do we set up the AI problem such that if the machine solves it, no matter how well it solves it, we are guaranteed to be happy with the result? So this is what I've been working on now for about a decade. And it's not the things we've been doing. The standard model that I mentioned at the beginning, where you provide a fixed objective to the system and it optimizes that objective, that does not work. When you go into the real world, it's impossible to specify the objective correctly. It's what we call the King Midas problem. King Midas wanted everything he touched to turn to gold. That was the objective that he stated. The gods grant his objective. Here they're playing the role of the AI system. And, of course, his food and his drink and his family all turn to gold. And then he dies in misery and starvation. And there are many, many other legends like this in many, many cultures around the world that be careful what you wish for. What we're doing with large language models is actually even worse. We're not specifying the objective. We're simply training them to copy the behavior of human beings. And I'll show you later why that's a really bad idea. So instead, the proposal is that machines have to act in the best interests of humans. And that itself is a complicated question. So I put 2 asterisks there, meaning this is a complicated question. But the important thing is those machines are explicitly uncertain about what those human interests are. And this is a significant departure from the way that we have designed AI systems in the past, where we always specify the objectives. So every chapter of my textbook talks about how the objectives are specified and then how you design algorithms to achieve that type of objective under those kinds of conditions. But here we're beginning from a different premise where the objective itself is unknown. And therefore, it's the job of the system both to find out more about what it is that humans want, but also to behave, then it's going to behave cautiously because it knows that there are things it doesn't know about what humans want, and therefore it should not mess with the universe unless it's pretty sure that that's how we want the universe messed with. And we can turn this into a mathematical framework that we call an assistance game. So it falls within the economic framework of game theory, which is decision problems involving 2 or more entities. So here, there's at least one human and at least one machine. The human presumably has some preferences about the future. They may not be complete, and the human may not even know their own preferences. And then there's a machine whose job it is to help satisfy the human preferences, even though it starts out not knowing what those preferences are. And I hope that from this explanation, you can see that the better the AI system solves this problem, the happier we are going to be. Because that basic issue of misalignment does not arise. And we can see by solving assistance games and looking at the solutions and analyzing the mathematics of this framework, that without having to be told, these AI systems will defer to humans. They will act cautiously, so this idea of minimally invasive behavior. They will change as little as possible about the world. And they will always be willing to be switched off. And this is a mathematical theorem. They have a positive incentive to allow humans to switch them off. And that's, I think, crucial to retaining control forever. And we can show that it's, in fact, in our best interests to build assistance game solvers. Even if we don't know what our own interests are, we should still build these things. But they have to be built very carefully, and there's a lot more theory that I haven't explained here. So over the past couple of years, here are some of the specific questions that we worked on. The first one is, what happens when either the human or the machine or both does not have full access to the state of the world? And if you were ever a child, I assume most of you were children at some point, and if your parents ever told you to tidy up your bedroom, which I assume they did, you probably figured that you could just shove everything under the bed and your parents wouldn't know, right? We don't want the AI systems to shove everything under the bed and try to fool the humans. So we have to make sure that that's not the solution to the assistance game when there is partial observability. And indeed, it turns out that the AI systems will not shove everything under the bed because then there's no guarantee that the humans believe that the AI system has actually solved the problem. We want to scale these things up so they can work on bigger and bigger problems, scale up to the real world. So we've got as far as Minecraft, so now you can have a little helper that is watching you while you're doing Minecraft and actually maybe even signaling with you to try to figure out more about what you want, and will quickly figure out what you're trying to do and help you do it. One of the most fundamental questions is this issue of plasticity of human preferences. So the fact that human preferences are not fixed, and we don't actually sort of autonomously choose our preferences. Right? In fact, the preferences we have about the future are not the ones we were born with. They're the result of our upbringing, peer pressure, our culture, everything else, as well as our biology. And so that means that AI systems themselves can manipulate our preferences. And I believe this is one of the things that's happening with social media, for example. So how do we make sure that the solution to the assistance game does not involve AI systems that manipulate human preferences? They can't avoid affecting our preferences because any form of interaction with humans is going to affect our preferences, particularly one that involves a super helpful household butler that does everything for you and helps you run your life. Of course, that's going to change your preferences. But how do we make sure that it doesn't do it in a manipulative way? And then the last thing actually harks back to what I was mentioning about the approach to AI based on knowledge that was prevalent from, let's say, 1965 until 2010. So during that period, this was simply an article of faith that intelligent systems should know things, that they should have internal knowledge that is a representation of the external world. That's what science does, in fact, is create those internal representations for the human race of the external world so that we can then reason and plan using that knowledge. But why is that a good idea? Why don't we simply learn an input-output mapping? Now, we know that, for example, for noughts and crosses or tic-tac-toe, it's a perfectly sensible solution just to build a lookup table saying if this is the position I'm in, then this is the right move. And that lookup table doesn't know the rules of the game. It doesn't know what the objective is, but it still plays perfectly. So the question is, why do we think that knowing things about the world is a good idea? And so the fundamental theorem of AI would be an answer to that question. And we're making some progress towards that and actually showing that for a very large class of mathematically defined environments, the sample complexity, meaning the rate of learning for a knowledge-based systems, is exponentially better than it is for simple input-output systems. And so if we can take this work further and generalize those results, that would actually be the basis of a beginning of a real scientific theory of intelligence, in my view. There's a lot more to do. We have to understand much more about real humans if AI systems are really going to learn about human preferences. And there still remain questions in social choice theory, how you make decisions on behalf of many human beings. And these problems in social choice theory go back thousands of years. They involve the theory of utilitarianism, which basically says everyone's preferences count equally, so you add them up. But then there are issues about egalitarianism. There are issues to do with decisions that affect how many people exist, and many other open questions. So I've outlined, I think, some of the dangers of achieving AGI and a possible route to solving some of those problems. Meanwhile, the AI companies are proceeding faster and faster with less and less concern for safety. So a few weeks ago, a group of OpenAI current and former employees posted an open letter and said that from their vantage point inside the company, attention to safety has been bypassed almost completely. And so a lot of the AI safety community are thinking about regulatory solutions. The difficulty we face is that it's hard to define safe and beneficial. For airplanes, we don't want the airplane to hit the ground until it's supposed to. Right? So it's a fairly simple definition of safety. For a nuclear power station, we don't want it to explode. We don't want it to release radiation. But for AI systems, because they're so general, the definition of safety is quite amorphous and culturally varied, geographically varied, and very difficult to define. So instead, we can actually define obviously unsafe behaviors. So they're way at the unsafe end. They're precisely defined. We call these red lines. And the onus should be on the developers, as it is on the developers of medicines and airplanes and buildings and nuclear power stations. The onus of proof is on the developer to show that their system is not going to cross these red lines as a condition of market access. And so we want these red lines, as I said, to be well-defined. Ideally, they should be automatically detectable. We also want them to be politically feasible so that the Prime Minister can explain to people why are we imposing these restrictions, and it will be difficult for the companies to get up in front of Congress or Parliament and say, well, yeah, we do have $3 trillion in the bank, but we can't guarantee that our systems are not going to replicate themselves. We can't guarantee that our systems are not going to advise terrorists on how to build biological weapons. That's, to me, an indefensible position. And so I believe we need these red lines. The effect would be that the companies would have to do the safety engineering that they have failed to do. Here's the situation that the companies are in, right? Imagine if the airplane manufacturers had decided, instead of doing all the engineering and the calculations of lift and drag and so on, had decided just to breed bigger and bigger birds. And then they come to the Federal Aviation Administration and say, well, we'd like you to certify this latest model. I should say this was produced by Dolly, this picture, and that's why the bird has 3 legs. And I think the FAA would say, look, these birds eat the passengers, they drop them in the ocean, we are not certifying your technology, come back when you have technology that you understand well enough to give us some high confidence statement about safety. So this is really the situation we're in right now, where the companies are unable to give any such high confidence statement because they are breeding their technology and they don't understand how it works. The next question. So we have a way of developing safe AI, we regulate to make sure that people use it. How do we prevent other actors, rogue actors, from deploying unsafe AI systems? Because they don't want systems that are beneficial to the human race. We call this the Dr. Evil problem. Dr. Evil doesn't want safe systems. Dr. Evil wants systems that will take over the world for him. So this is a really difficult problem. Policing software, as we have found out with both accidental mistakes with software and with deliberate malfeasance with software, is very, very difficult because it's produced by typing, and it's transmitted at the speed of light, and it's copied infinitely. So what we actually need is the hardware to be the regulator here. And the reason for that is that hardware is incredibly expensive to produce. For a rogue entity to reach the hardware capabilities of NVIDIA and TSMC would cost more than $100 billion, at least a decade, and would require probably tens of thousands of highly trained engineers. So if we can get the very small handful of hardware manufacturers to agree, as in the past we did with digital rights management, then we can turn the existing model, where the hardware runs anything, to a new model where the hardware says, nothing runs unless I know it to be safe. And there's a technology called proof-carrying code which allows this to happen. Proof-carrying code means that the software object comes with a proof of whatever property you need it to have, and that proof can be checked immediately and quickly by the hardware. And so the hardware refuses to run software objects that don't have a proof of safety, and then the software objects refuse to run on hardware that isn't checking that proof. So this requires a lot of lifting, as you can imagine, because it means replacing our entire digital infrastructure. So to sum up, I think AI has vast potential to benefit the human race. It has unstoppable momentum. But if we continue on the path that we are following, we will lose control over our futures. So the only option, I think, for us is to develop a technology of AI that is provably safe, provably beneficial to us. And so rather than thinking about making AI safe, which sort of means making AI and then thinking about how to make it safe, which I think cannot be done, we have to think about making only safe AI. Thank you.
Thank you so much. Thank you so much, Professor Russell, for sharing your fascinating and thought-provoking insights and perspectives today. Thank you very much.
Pleasure.